Welcome to this second lecture on mathematical logic. In the previous lecture, we have discussed about the propositional logic, the concepts of propositional logic. We have discussed about what are propositions, right? Just to have a quick recap, a proposition is any assertive English statement which can have a truth value of either true or false, right? So any statement that can have a truth value of true or false is called a proposition. So for example, 1 plus 2 is equal to 5, even though it is not true, but it is still a proposition. The year is 2020. So this statement having a truth value of true is also a proposition. But if I say a statement like, let us say, come here, this statement, as it is not an assertive statement, is not a proposition, right? If I say something like, let us say, x plus y is equal to 5, now this again statement, the truth value of this statement will depend upon the respective values of x and y. So there is an ambiguity. So once again, this is not a proposition. So a proposition is any statement that has a well-defined, clearly defined truth value of either true or false. We also saw the various connectives that are used to combine two or more atomic propositions into compound propositions. Now the various connectives that we discussed in the last lecture included the negation, represented by this symbol, right, which is used to negate the value of a proposition. So if we have a proposition whose truth value is true, the negated proposition will have a truth value of false and vice versa. Then we have the conjunction, which works like the AND operation, right, denoted by this symbol. We have the disjunction, which works like the OR operation and is denoted by this symbol. We also discussed the exclusive OR operation, right, which is denoted by. We also saw that the propositions can be either represented in an informal manner or a formal manner. Informal manner means a simple English statement, and formal manner means it's a mathematical statement. I can give you a statement like, the year is 2020 and the month is August. So the statement, this part of this atomic proposition can be represented by, let us say, P, and this atomic proposition can be represented by, let us say, Q. So this proposition, this is a compound proposition in an informal manner, which can be represented in a formal manner like P and Q. So we can have a proposition in either the informal manner or the formal manner. So in this lecture, we are going to discuss about certain other connectives, and we will talk about the logical equivalence and how to verify, how to negate the various compound statements, right? Let's continue. So the next connective that we are going to talk about is the implication. Now the implication essentially is a conditional promise. So implication is essentially the formal way of writing the if then statement. So this is akin to saying if something, then something else. Now this part and this part both are the propositions. Say for example, if I say if I'm on campus, this comma is actually representing then. If I'm on campus, then I study. Now, if this part of the proposition, this atomic proposition is being represented by P and this atomic proposition is being represented by Q, then this compound proposition, if I am on campus, then I study, is represented by P implies Q. This symbol is called the implication symbol. This is also called the conditional. If I take one more example, let us say, if we say, if we develop a vaccine for coronavirus, then we can open the schools, right? So this part of this atomic proposition, we develop a vaccine for coronavirus, if this is being represented by, let us say, v for vaccine, then we can open the school. If this atomic proposition is being represented by, let us say, school, s for school, then this entire statement can be presented by v implies s. If v, then s, right? So we write it as if p, then q. If the value of the if part is true, then the value of the then part must be true for the implication to hold. We say that the implication is holding if the value of the compound preposition, this value of this compound preposition is true, right? in this compound proposition, the P part, when we say P implies Q, this if part is called the assumption or the premise or the antecedent, and this then part Q is called the conclusion or the consequent. So this is the premise, this is the conclusion. Now this is the truth table of the implication, right? Please remember, as I told you earlier, that implication is similar to a conditional promise, and the only way a conditional promise can be broken is if the if part is true and the then part is false. If I take this example, if I talk about this example, if this is a, let us say, a conditional promise, the only way this conditional promise is being broken is if the vaccine for coronavirus is developed but the schools do not open. Here, if we develop the vaccine but we are not opening the schools, that is the only possibility, that is the case when we are breaking our conditional promise. Now let's see it from a truth table point of view. See, if I have P and Q, two atomic propositions I have, now I have four possible values for these two atomic propositions. Both of them are false. If part is false, then part is true. If part is true, then part is false. If part is true and then part is right. This implication is false, or this conditional promise is broken only when the premise is true but conclusion is false. If the vaccine is developed but the schools are not opened, right? So you can see over here, when the premise is true but the conclusion is false, that is the only case where the this implication is false. Otherwise, in all the three other cases, the conclusion is, the implication is true, right? Let's think over it a moment. Let's rewrite it over here. If a vaccine is developed, then the schools are opened, right? Let's talk about this statement in terms of this truth table. We say if a vaccine is developed, we are representing it by P, and schools are opened, we are representing in terms of Q. Let's talk about, let's discuss or analyze this compound statement in terms of the truth table. We say if a vaccine is developed, then the schools are opened. If, let us say, the vaccine is developed and the schools are opened, then we say this is true and this is true, so the implication is holding. If the vaccine is not developed, let us say if the vaccine is not developed, God forbid, if the vaccine is not developed, then if the schools are opened or not opened, we cannot say that the conditional promise is broken. Why? Because the premise has not yet been affirmed. If the vaccine is not developed and the schools are opened, or if the vaccine is not developed and the schools are not opened, in both the cases, we cannot say that the conditional promise is broken. So in both the cases, the implication holds, right? Even if here both the premise and the conclusion are false, but the implication is still holding. It is only when the vaccine is developed but the schools are not opened, true and false, it is only this case where the conditional promise is broken and the implication becomes false. That means P implies Q does not require that P or Q are even true. I can even have a statement like this: 1 implies, sorry, 1 is equal to 0 implies that the year is 1920. So this is, let us say, false, sorry, this is false and this is also false. But the implication, false and false, you can say the implication is still true, right? If the premise is false, please remember, if the premise is false, then irrespective of the value of the conclusion, the implication will always be true. But if the premise is false, then, sorry, if the premise is true, then if the conclusion is true, implication holds. Premise is true and conclusion is false, then the implication fails, right? Let's see some more examples of implications, right? I have once again made the truth table of the implication over here. Now we have four possibilities which are actually representing the four rows of this truth table. Let us call them row 1, row 2, row 3 and row 4. Right? If the year is 2020, True. Then the sun will rise tomorrow. True. So this particular example is talking about row number 1. So obviously the implication is true. If Tuesday is a day of week, true, then we are on the moon. I hope this is false, right? So I sincerely hope that all of us, I imagine that all of us who are viewing this video are still on earth. So the premise part is true and the conclusion part is false. So this is the only case. This is we are talking about essentially row number 3. So this is the case where the implication is false. If 1 plus 1 is equal to 6, this is false. Then we are facing the corona pandemic. This is true. So we are talking about row number 2. So still the implication is true. If the moon is made of green cheese, then I am richer than Bill Gates. Kash aisa hota. So if the moon is made of green cheese, false, then I am richer than Bill Gates. Once again, false. So we are sorry, I made a little mistake over here. This was row number 4 and this is row number 1 over here. So this is row number 4, this is row number 1. So again, this is false, this is false. So still the implication will be true, right? So these are the some of the examples of implications. Now, when we have defined an implication, P implies Q, now I can define 3 more conditionals based on this implication, right? If I have P implies Q, then I can define the converse as Q implies P, the inverse as not of P implies not of Q, and contrapositive as not of Q implies not of P. Using the same example, right? Let's take the same example. If vaccine is developed, then schools will open, right? If this is the original implication. Now, what will be the converse? If schools will open, then the vaccine is developed. What will be the inverse? If vaccine is not developed, then the schools will not open. And what will be the contrapositive? If the schools will not open, then the vaccine is not developed, right? So from the original implication, I can define the converse, I can define the inverse, and I can define the contrapositive. Now, out of these 3, or out of rather these 4, the implication P implies Q, the converse, the inverse, the contrapositive, 2 of the compound prepositions have the same meaning. Now, when I say they have the same meaning, what I mean is they have the same truth table, right? Can you imagine which is which? That is the contrapositive. Now we can verify that the contrapositive has the same meaning as the original proposition by making the truth table. Let's take the example. Now this is the implication PQ. P implies Q. Let's make the truth table. Please remember the implication will be false only when the if part is true and the then part is false. So P implies Q. This is the only case when it is false. Now what will be the contrapositive? Contrapositive is not of Q implies not of P. The same symbol, I can also write it like this: not of Q implies not of P. Both the symbols are valid. So not of Q, I have the Q over here. The negation of this will be when it is false, it is true. When it is true, it is false. Similarly, the negation of P, for false, it is true. For true, it is false. Now, not of Q implies not of P, right? So once again, please remember this implication will be false only when this is now the if part, this is now the then part, when this is true and this is false. So this is the case when this is true and this is false, then this implication will be false. In all the other cases, the implication are true. So you can see, so you can see that both these truth tables for the P implies Q and not of Q implies not of P are same. So P implies Q. So I can say that P implies Q is same as not of Q implies not of P. In fact, you can even verify that the converse Q implies P is same as not of P implies not of Q, the inverse. So the converse and the inverse are equivalent to each other, right? You can see the inverse is actually the contrapositive of the converse. You can see it over here. See this, we have P implies Q and the contrapositive is not of Q implies not of P. The converse is Q implies P and the contrapositive of this converse will be not of P implies not of Q, which is nothing but the inverse, right? You can make the truth table to verify that these two are logically. We have the biconditional. The biconditional is essentially the if and only if promise. If P and Q are two propositions, then P biconditional Q. This is called P if and if Q if and only if P. It is a biconditional proposition. P if and only if Q. P if and only if Q. Right? P is called the necessary and sufficient condition for Q. What it means is if P then Q, that means P implies Q and vice versa. That means and Q implies P, right? This is what is meant by biconditional. It means P implies Q and Q implies P. You can appear for the exam if and only if you fill the exam form. You fill the exam form, you can apply for the you can fill the exam form, you can appear for the exam. You do not fill the exam form, you cannot apply for the you cannot appear for the exam. So we can say that P biconditional Q is same as writing P implies Q and Q implies P. Let's see the truth table, right? Let's see the truth table. P Q, right? So biconditional, if you say the biconditional is true, the biconditional is true when both P and Q have the same value. They can both have the same value, either it is false or it is true. In both the cases the biconditional is going to be true. In the two remaining cases the biconditional is false. So P biconditional Q means that P and Q have the same truth value. Now please see, if let us say I make the truth table of P XOR Q, right? False, 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 true, true, false, true, true. If you remember, we discussed that the XOR is true when the P and Q are different. So this was false, true, true, false. Now if you compare this with this, you can see that this truth table for a biconditional is the exact opposite of XOR. So I can say that P biconditional Q is the negation of P XOR, right? This is another way of writing P biconditional. Let's summarize the various Boolean operations that we have talked till now. If I have two atomic propositions P and Q, I can perform the different Boolean operations or logic operations. Boolean operation or logic operations, essentially they are interchangeable. The words are interchangeable because in both the cases we are working only with two values, true and false or 1 and 0. So this is the negation operation, conjunction operation. This was the disjunction operation. This was the exclusive or operation. This was the implication, and this is the bicondition. So this is a summary of all the operations. This is the truth table for all the 1, 2, 3, 4, 5, 6 operations that can be performed on the propositions, atomic propositions. Now let me introduce a couple of new terms over here: tautology and contradiction. A proposition that is always true is called a tautology. A proposition that always has a value of true irrespective of its constituent atomic propositions is called a tautology. A proposition that always has the final value of false irrespective of its constituent atomic propositions is called a contradiction. Now we also have a third type of compound proposition which is called a contingency. That means a proposition which is neither a tautology nor a contradiction is a contingency. Let us say P and Q. Now Depending on P and Q, this might have some values of true and some values of false. So this is called a contingency. The tautologies and contradictions are quite important when talking about the logical equivalences, or when we'll be talking about the validity of arguments. So please keep this in mind. So a proposition which is always true is called a tautology. A proposition that is always false is called a contradiction. Now, logical equivalence. Say for example, I have a compound preposition, let us say capital P, and I have a compound preposition, let us say capital Q, right? I'm using capital letters over here to represent the compound prepositions. Now this preposition P could be made up of a number of atomic prepositions. Similarly, this can also be made up of a number of atomic prepositions. Now these two compound prepositions are said to be logically equivalent and are denoted like this, or in some texts like this, if both of them have the same truth table. If both of them have the same truth table, or we can say if the compound preposition capital P biconditional capital Q is a tautology. So to verify whether these two prepositions, these two compound prepositions are equivalent or not, you can either make the truth table, and see that both P and Q will contain the same truth values in all the rows, or you can use this to verify that it is a tautology. You can make a truth table of capital P biconditional capital Q and see that all the values in the final row will be a final column will be a truth value of true. So you can either use this method or you can use this method to check for logical equivalence, right? Let's take a simple example proving equivalences via truth table. Let's say I have this expression over here P disjunction Q, and on this side I have negation of P conjunction negation of Q. Now I say that these two statements are logically equivalent, but how do we verify it? So the simplest way is to draw the truth table of the two sides. So PQ, so this is the truth table for the LHS, and for RHS I'll make negation of P, negation of Q. This is the truth table for this part, and this is the truth table for the entire RHS. Right? Now you can compare this part with this part. You can compare this, the truth table for the left hand side part and the truth table for the right hand side part, and you can see that it is false, true, true, true. It is also false, true, true, true. So we can say both the truth tables are same. So we can summarize, or we can infer from this that both the sides, or this expression is logically equivalent to this expression. Similarly, if I say P XOR Q, if I say this P XOR Q is logically equivalent to P or Q and not of P and Q, once again what you can do is you can make the truth table and you can verify that the truth table of the LHS is same as the truth table for the RHS. So this tells me that both the statements are logically equivalent. So the important point to take from here is a particular logical formula can be written in multiple ways. A logical formula can be written in multiple ways. Now this becomes very important for us when we try to negate these statements. Now negating this statement directly becomes difficult, or negating a statement which involves, let us say, implications or XOR or biconditionals directly becomes difficult. So what we can do is we can write these statements into their equivalent forms where the negation becomes comparatively easier, right? So now this implication P implies Q, right? If you make the truth table of this implication, it is, once again I'll repeat, the conditional promise is broken only when the premise is true and the conclusion is false, right? Now, if you remember in the previous lecture, we said that from a truth table, you can write an expression by using two ways. Idea number one was to take all the true values from the truth table and then take the expressions and put an or in between them. Right? And the second idea was to take the false value, take the expression for the false value and put a negation over them. So we are using this over here. So this implication can be represented like this also. Negation of P or Q. Right? I can write it over here. Or there is another way. What you can do is you can write P implies Q is logically equivalent. If I use idea number one, I can write it as P and Q, or taking this particular row, negation of P and Q, or taking this row, negation of P and negation of, right? In subsequent slides, I'll show you how to simplify this to come up to this particular conclusion. You can use the methods that I'm going to explain in a short while to verify that this will obviously come down or get simplified into this expression. So the main point over here is P implies Q is logically equivalent to negation of P or Q. Now this is an important result. Now another way is by using the equivalence laws. We have certain laws which have been defined on the connectives that are used with mathematical logic, and there are laws which govern the operation of those connectives. Now before we go into the equivalence laws, please understand that these equivalence laws are also governed by the law of duality. Right? Duality means, just as it meant in the case of Boolean algebra or set theory, that the dual of a particular law can be obtained by interchanging conjunction with disjunction, by interchanging true with false. So if I have a particular law, I can obtain the dual of this law by interchanging conjunction and disjunction and true with false. So the various laws are, first one, I have the idempotent law, which says P or P is equivalent to P, P and P is equivalent to P. Now these are the dual of each other. I have obtained the dual by interchanging the or with the and, the disjunction with the conjunction. I have the simple commutative law. I have the simple associative law. Once again, P or Q or R is equivalent to P or Q or R, right? P and Q and R is equivalent to P and Q and R, right? Distributive law, which says P or Q and R is equivalent to P or Q and P or R, right? Distributive law actually requires, it can be only performed with minimum two operations, or and both are required over here. Similarly, P and Q or R is equivalent to P and Q or P and R. Now these laws, this law and this law, are dual of each other. They have been obtained by interchanging conjunction with disjunction and vice versa. Next, I have the involution law, and this is the only law that is not going to have any dual. Why? Because it does not involve any conjunction, disjunction, or true or false. It simply says negation of P is equivalent to P. So obviously, if I have a proposition P, the value, if it, let us say the value is true, the negation of P is going to be false. If it is false, then the negation is going to be true, and negation of P is once again going to be true. So this is same as this. So again, negation of P is going to be false. Once again, this is similar to this. So this is the involution law. Then I have the identity law. P and true is equivalent to P. Let's see this one. If I have P and true, let us say P can have two possible values, true, false, right? So this is true, this is true. This is the AND operation, conjunction operation. True and true is going to be true, which is same as P. False and true is going to be false, which is once again same as P. So I can write P and true is equal to P. The dual by interchanging conjunction with disjunction and true with false is P or false is equal to P. Then I have the domination laws. Then I have the De Morgan's laws, which are quite important, as we'll see in subsequent slides. They are very important when talking about negations. It says negation of P and Q is equivalent to negation of P or negation of Q, right? When we open this bracket for negating, this negation is applied to both the atomic propositions, and the connective combining these two propositions is interchange. This is reversed. If it is a conjunction, it becomes a disjunction. If it is a disjunction, it becomes a conjunction. Then I have the trivial tautology or contradiction laws. Right? Now, these laws can be verified. We just don't take our word for it that these laws are truths, but these laws can be verified with the help of truth tables. I'm verifying one of the laws with the help of a truth table. So once again, what we do is we have one of the De Morgan laws which says negation of P and Q is equivalent to negation of P or negation of Q. So what we are going to do is we are going to make the truth table for the LHS, we are going to make the truth table for the RHS, and we will show that both the truth tables are same. As you can see it over here, this is the truth table for the LHS part, this is the truth table for the RHS part, and you can see both of them are same. So we can verify this law with the help of truth table. In fact, we can verify any and all of these equivalence laws by using the truth table method. So I suggest you verify all these equivalence laws by making truth tables of LHS and RHS, left hand side and right hand side of the equivalence symbol, and verifying that the truth tables on both the sides of left hand side and right hand side are equivalent. So I hope you do it so that you can actually verify that these laws are valid. How to use the laws for simplifying the statements, right? Let us have this. I have this compound statements which says negation of negation P conjunction Q conjunction P disjunction, right? Now I'll simplify this statement by applying the different laws, right? First of all, I'll apply the De Morgan's law over here, right? If you remember, what was the De Morgan's law? De Morgan's law says negation of P Q is equivalent to negation of P or negation of Q, right? So applied over here, negation of negation P and Q. So this becomes negation P or negation Q, right? There was one negation already over here. So next I apply the involution law, right? If you remember, what was the involution law? Involution law was negation P is equivalent to P itself. So I have P or not of Q and P or. Next, we are going to use the distributive law. If you remember the distributive law, what was the distributive law? P or Q this is equivalent to R and P, or I can write R or Q, right? Now if you see over here, if you see over here, P or not of Q, P or Q. So I have a P over here, I have a P over here, I have a R over here, and I have a R over here. Now if I take R common from both the sides, if I apply the distributive law in reverse, that essentially becomes R or P and Q. So that is what I am going to do over here. So I get P or not of Q, and once again I apply the law over here, this becomes false. You see, not of Q and Q, right? Not of Q and Q. If this is true, this is false. If this is false, this is true. And if I'm performing the AND operation between these two, the resultant is always going to be false. So I have P or false, right? Now I have a OR operation over here, P or false. I can have true over here or false over here. This is false and false. Please see the resultant True false is true, false false is false. So whatever is the value of P will be the resultant over here. So it is equivalent to P. So this complicated looking compound statement is in fact equivalent to our simple atomic proposition, right? So in this way, by applying these laws, you can simplify the statements. Before we proceed further, we can rewrite exclusive or implication or biconditional by using their equivalent forms, right? You can see over here XOR can be written as this or this, like P XOR Q is logically equivalent to P or Q and not of P and Q, or it can also be written as P and not of Q or Q and not of P. Similarly, P implies Q. This one we have already proven with the help of a truth table. This can be written as not of P or Q. Similarly, biconditional can be written as P implies Q and Q implies P. Then you can further convert it. You can further rewrite it like P implies Q. P implies Q becomes not of P or Q, and Q implies P becomes not of Q or P, right? So you can further rewrite it in terms of the basic operators, basic connectives. Similarly, here also P biconditional Q, you are writing it in terms of not of P XOR Q. This can again further be converted into, you can write negation of P or Q. If I use the first expression, P and Q, and like this. So this way you can rewrite this biconditional in terms of the very basic tips, right? Now this becomes important when we are talking about, so this again can be written like this also. You can once again convert it into further elementary property like P or Q, negation of P or Q, or P and Q, using this and this property. Now this becomes important when we are talking about negation of compound propositions. Now there are certain rules to be followed for negation of compound propositions. The first rule or the first point is that De Morgan's theorem are very low. The De Morgan's laws are very important while performing the negation. Once again, to recap, the De Morgan's laws are negation of P and Q is equivalent to negation of P or negation of Q. Negation of P or Q is equivalent to negation of P and negation of Q. Second important point, before negating the exclusive or conditional or biconditional, if they must be converted to their equivalent forms, as we have discussed in the previous slide. So they can be written like this or like this. Once again, this, if I am using this, it can be rewritten as, right, you can say P or Q negation of this, or P and once you have written it like this, now negating this statement becomes easy. So let's have a simple example. If I want to negate an implication, it simply says P implies Q. Now I want to negate this. So before negating, what I'll do is I'll rewrite it as its original form, the alternate form, sorry. So negation of P or Q, now I can negate it. First of all, what I'll do is I'll apply the De Morgan's theorem. So that will become negation P and Q. Involution will make it P and not of Q. So this is the negation for the implication. What it actually means is, if I write a statement like, if my computer is not working, then I cannot finish my homework. So if I call this statement, my computer is not working, as P, and I cannot finish my homework as Q, right? So this is P implies Q. Now if I say, if I ask you to negate this, then it becomes P and not of Q. So my computer is not working. P remains as it is, but Q is negated and we combine them by using a AND. So I can finish. I cannot finish becomes negation of Q. So I can finish my work. So this was about the conditionals and the biconditionals and how to perform the negation. And we also discussed about the various laws, logical equivalence laws, right? Next lecture, we are going to talk about the arguments, the validity of arguments, and the ways of checking the validity of argument. Till then, thank you.